water and sewer stuff. Always a fun time. So someone remind us what Boston is built. Do you remember that? A what?
The salt marsh.
Okay, good, the salt marsh, yes. Anything else? Yes. Remember this landfill project? So Boston has a storied environmental history, and it's been described as a reverse Atlantis. So instead of a city diving down beneath the ocean, it emerged from the ocean, not just miraculously, but as a result of some large engineering undertakings in the 1800s and beyond. So what happened was we started to fill in, right, this former salt marsh. This is a picture of the original area of Boston in white. So that's how Boston was. It was referred to as Tremont, which is 3 mountains. There were 3 little hills in this white part here, looking like a sideways clover, and a dirt road going out to it. It was a very small city. And as we will see, pressure for increased building led us to fill in different areas. West Cove and Mill Pond were filled in first, and then we filled in the largest area, Back Bay. It's a huge undertaking. And then filled in other areas. As late as 1922, we were filling in the area where Logan Airport is now. So when you hear this word landfill, it's a common misperception to think that we're throwing trash in there. But what we did was to lop the top off of Beacon Hill, to bring sediment from as far west as Framingham, and dump it into the salt marsh, right? Back Bay, what we call a terrestrial region of bay. So in this way, we have built up a lot of Boston's landmass, which will come with some environmental challenges, shall we say, as well as engineering challenges. And one myth that I'd like to dispel here. How many of you have heard that Boston's roads make no sense because they were cow paths? Okay, so that's not the case. The reality of the situation is that the roads really started to be implemented pre-development here, and the roads sought to avoid the bay, right? I'm going to drive a road into the bay. So they sought to sort of ring the coastline, and then also to avoid the hills. So they were going along in these areas that were between the big hills and the coastline. So it's nothing to do with cow paths. It has to do with land use and land use changes through time. So we also, remember, right? We created the Mill Dam. You see these connections with the other things we've talked about in this class. The Mill Dam was a really long dam that went across the area where you see Back Bay. And what that did was to stagnate the waters in the tidal marshes. I could lift it up a little. Thank you. You know, I always have tech tools. Good, better? Better? Yes, I can. It's not on? Shall I shout? Shall I talk into here? Well, no, it's because of that. Better there? Okay. All right. Now we have to move that away or we'll get ringing, which will annoy you and wake some people up. So this, not too loud. That's distracting. This is too loud. It's too loud. Yes, too loud. I sound like God. Okay, better? Okay. So this dam was constructed in an attempt to harness energy. Remember we talked about early dams being a way of obtaining power. And the dam failed to produce power, still too loud, in any meaningful way. But what it did was to stagnate the waters in the Back Bay area. You have this tidal mudflat. We talked about marshes, tidal mudflats. And what else was going on to make this even worse? What made it smell even worse? What? Huh? Manure? Well, sort of, yeah. Human manure, right? We were discharging untreated sewage into the tidal mudflat, which smells bad anyway, right? It's emergent tidal mudflat. You put in a bunch of human sewage, and then you block off any means by which we can replenish that water and allow the water from the ocean to attenuate the pollution. You had people literally fainting in the streets from the smell. So this was a crisis. We have a disgusting, nasty city. We have a failed means by which we can get energy. And now we have the next problem of water. Where was Boston going to get its water? In the 1920s, we had a big population increase, and it became apparent that we weren't going to be able to meet the needs of the water supply for people in Boston.
mostly because we were pretty much destroying all the quality of the water because of our discharging of human sewage. So engineers started to look farther and farther west in an attempt to hit upon a reservoir that we could use to pipe water into Boston and provide the residents with good quality water. And we looked farther and farther and west. We had a couple, Wayland and Natick, there were little ponds that we could use. Early in Boston, we used Jamaica Pond, and we had cisterns, we had wells. We talked about groundwater. We eventually hit upon a river way over here called the Swift River. And the Swift River, it was deemed, was excellent quality water. And it was large enough so that if you dam it, and we also talked about dams, you can provide a stable supply of water. Right? You don't want to draw water from a river that's going up and down all the time for a major metropolitan area. So we found this river, the Swift River. So there's Boston. We had these, this is today. So we had these reservoirs that we used on the way out to our big main reservoir called Quabbin. What was the problem with making Quabbin? I mentioned this in passing when we talked about dams and reservoirs. What was out there on the Swift River? Yes, excellent. Small towns, right? So in 1922, a study officially endorsed the Swift River as the next extension of the water system for Boston. And so people were saying, okay, here we go. And the MWRA, Mass Water Resources Authority, was created to oversee this and to construct the first project, a tunnel connecting the Wachusett Reservoir to the Ware River, and then eventually out farther and farther west. Interesting that the pipes that were connecting Boston with these increasingly farther away, now we're at Quabbin, which is about 100 miles away, water sources, was hollowed out logs. So we buried hollowed out logs. These are the workers who are starting construction on the dam for the Swift River, and started to bury these hollowed out logs all the way out to Boston. That poor dog, he's probably dead now. Should feel sorry for him. Here's the first town, Dana. Dana was incorporated in 1901. So it was, quite some time that people were living there in Dana. And the last meeting, as you can see, was held in 1938. The road to Dana, you can still see, it's still paved. It's sort of ghostly to go out to Quabbin. You have these roads that go out to what was once a town. You can see the cellar holes for the buildings that were moved. And you can see the foundation for the town hall. And the Dana poorhouse was there as well. So this is a town that was incorporated in 1801. The population was about almost 1,000 by 1860. And so it's the best preserved of the four towns. Enfield had also a population of 1,000. It was the most southerly of these towns. And people had moved. This town didn't have a lot of natural resources as the other ones did that we'll talk about. So people had moved away from Enfield and Enfield. And there were only about 2,000 people, only about 200 people living by the end of Enfield's time. To add insult to injury is a little sort of historical background. The United States military, when it was found that they were going to condemn Enfield and it was going to slip underwater, they started testing artillery, heavy artillery, during World War II. So they were bombing out the buildings to test for accuracy of the bombs, the big artillery guns, firing right into their town as it was flooding. And in 1937, they had a farewell ball at the Enfield Town Hall, and there were about 1,000 people that came from all of the four towns. They crammed in there, and a few minutes before midnight, they tolled a bell, and the band played Auld Lang Syne, and people were weeping as they marked to the end of the Enfield town. Greenwich, too, there's some selectmen that are erasing, they have smiles on their face, I guess, Enfield from the map. It was the oldest. It was incorporated in 1754, and there were population peaked at about 1,500. The thing is here, there were a few mills in the town, and there was agriculture because it was in an arm of the Swift River, so they had good agriculture. So it was a wealthier town. There were also a lot of rivers and lakes and streams, so there was a high tourist population there. So it was a wealthy town. You can still see the golf course that sits on a little high point on the Quabbin there. And the last interesting thing, again, threading through our course, talking about mineral resources, there was a bit of a gold rush in this town. There were these brothers, the Barlow brothers, and they were in the water near their house. They were working near a stream. They found some particles of gold. And they said, oh gosh, maybe there's gold here. And so in their spare time, they went to this granite ledge and they started drilling for gold. And in the early 30s, they found another vein. They found a vein of gold that was pretty decent quality. It was about, not tremendous, but pretty decent quality. And then in 33, they found another one that was gold and copper. And they were really excited about this because there was a hint that Prohibition was about to be over. And so copper was used to make the stills for making alcohol. So they dug and dug looking for gold and copper and never made a huge amount, but made a decent amount. And there is Prescott Town Hall. So those are the 4 towns that were buried. And this took almost 10 years. Construction started in 1930 and was completed in 1933. And there's a picture from 1989, which is, I think, a nice picture that shows the towns and how they were gone towards the end of us having a stable, excellent quality water supply. It's now the largest inland body of water in Massachusetts. And it's the primary water supply for Boston as well as 40 other communities in the greater Boston area. Remember a couple classes ago we talked about California's water problems, right? How there's not enough water to go around and the fisheries and northern versus southern and agriculture. You remember this? Yes. So this is not a blanket situation that water transfer is a problem, as it is in California. We have so much water here in Boston as a result of transpiration being lower than precipitation that we are able to supply Boston, 40 other communities, and then also the water's piped out farther west. And we actually retired a couple of reservoirs that were considered drinking water. The Cotuit Aqueduct was abandoned, the Framingham Reservoir System was abandoned and is now a swimming and boating resource. So in '85, Mass transferred possession and control of the operation of this to the Mass Water Resources Authority, and so it has governance over all of these transmission lines throughout the metropolitan area. In terms of quality, we looked at this, right? We looked at maximum contaminant levels and maximum contaminant level goals, and I tried to freak you out by saying that there are graveyards in the Quabbin Reservoir. We have in Boston excellent, excellent water quality. The United States EPA established, you may recall, the maximum contaminant levels for all sorts of criteria pollutants, and you can see here the maximum contaminant level, highest allowed from the US EPA. The state governing body is the Massachusetts Department of Environmental Protection. They're allowed to make the laws more stringent, so lower maximum contaminant levels. They're not allowed to relax the standards. So these are the maximum contaminant level goals. We talked about reaching towards those. And you see that for Boston, we have very good quality water. It's excellent quality water. And if the regular ongoing testing showed any exceedance of things like bacteria, lead, heavy metals. We also look at herbicides and pesticides, right, the things of agriculture that we talked about, as well as any industrial solvent. Then customers have to know, they have to be notified, local news media has to be notified. And when's the last time you were notified that your water quality is poor? Haven't, right? So we have excellent quality water. Does anyone remember the one thing that you may have to look at with regards to your building itself? Lead, right, exactly. So it was the case in the 30s and 40s that we used lead pipes to bring the water into older homes, and specifically lead solder, which can be mobile in water. And so you can have elevated levels of lead, which is neurotoxic to babies, to people. The only thing you need to do if you're worried about this, if you have an older home, if you live in an older home, is to turn on the tap water and let it go till it runs cold, and that will remove any lead from the water. So that's our water. Happy picture, great picture. We have plenty of water and it is excellent quality in Boston. Where does our water go? So once you use the water for showering, for washing your dishes and your clothes, for using the toilet, where does it go? We have one of the oldest sewer systems in the country. Boston has been using sewers since before 1700. The first sewers were privately owned and they were used to essentially pump water out of cellars. We're a coastal area. Remember that sea level is in hydraulic connection with groundwater, so people had to pump water out of their basement and they would discharge it into these sewers. that started to cause contentious relations between neighbors as there was too much water. People are discharging it into main waterways. So in 1709, the Mass General Court started to regulate the construction of sewers, and it also provided a basis for distributing costs for sewers. So now we're starting to see some quasi-public sewers. Then in 1833, with the advent of the toilet and or the proliferation of the toilet, I should say, they started to allow sanitary waste into the sewers. So the old sewers used to be storm water mixed with sewer water, right? Sanitary water. The newer ones separate those out, and so you have combined sewer and sanitary, which is about 20% of our pipes in Boston. 80% are separated out. So storm drains take water when it rains out to waterways, and the more hazardous stuff goes out to Deer Island. So the sanitary waste being allowed into the sewers back in 1933 caused a lot of problems. The town of Boston was trying to get people to take rainwater from their roofs and dump it into their sewers to try to flush stuff out into the ocean, but it didn't work, and we started to have health problems. We started to have cholera, typhoid, dysentery, because these sewers are really kind of problematic. So Boston created something called, this is off again? Created the, sorry people, did I do this? Yeah. Created the Boston main sewer system. And so this is a picture of one of the older sewer systems, sorry. We have this. Is this on? This is a little Las Vegas-y for me, yeah. So the present condition now is we have these sewers in Boston that are buried. We're trying to replace them. This replacing of these ancient sewers, some of which have been here since the 1700s, makes the Big Dig look like child's play, because we have to essentially dig up underneath all of Boston and to bring this water to Deer Island, which we'll talk about in a minute. So here's Deer Island. This is a part of the Boston Water Sewer Commission. They own and operate this system of collecting water, and about 70% of the land area for Boston goes out to here. We're trying to improve this all the time. Those egg-shaped digesters that you see from the plane when you come back to school after break or wherever it is you go are methane digesters. I need an extra hand, right? Those are intended to cause the wastewater treatment plant to be self-sufficient with regards to energy. So remember, methane is what? What do you know methane as from fossil fuels? What type of? Natural gas, excellent, yeah. So harvesting the methane as a byproduct of the human waste is natural gas. There are also some sorts of initiatives to, sorry about this, people, to use this waste. Where does it go now? You remember this? Where does this waste go? The sewage sludge that comes off of the wastewater treatment plant. Remember? Massachusetts, we're not allowed to use human waste on agricultural land unless the products of the agricultural land are fed to animals, right? So where does our waste go? You remember? Florida, right. We ship it down on rail car down to Florida, and they put it on the orange groves. So, right, it's exactly what's going on. You may think that's gross, but as we have these sustainability challenges, we need to make problems into solutions. And Obama has started to look at taking human waste and turning it into some sort of agricultural fertilizer. So, good. Problems, drama. The sewers are so old that we don't really even have good maps. So this is an aside, again, putting these connections in with energy and water resources. So there were a bunch of ministers from different churches around in Boston that were actually jailed because they were protesting the fact that this energy company was coming in, burying natural gas pipelines and breaking the sewers because they didn't know where the sewers were. And so you had these ruptures, you had flooding locally. And so, yeah, things got so heated that ministers were actually jailed for protesting this mixing of energy and water. It's the oldest and most fragile system in the nation, and it's in crisis. When these pipes break, people say that you're at increased risk of GI diseases that occur from drinking water flowing through the pipes that are too old to safely carry water. So small side note on the toilet, which has, water and sustainability ramifications. It used to be in Boston that people just had these commodes, so you had this chamber pot. That was replaced by something similar to, I guess, a cat litter box. There were little rooms, and they had granular clay in them, and there was a lever. And you went in and did your business, and you pulled the lever over, and you buried the waste. So there were these clay layers in a little room. And then eventually, in the 1800s, we started to develop these toilets, which were historically ornately colored, and the plumbing was such that you had a tank way up high and had this pull chain, and the water would come down and flush out the waste. So in the 19th century, people didn't even have their own toilets. They had to share one. Sometimes you had to be in a line to use a toilet, and it was a big thing. These days, a couple of things to note as we move into the problems of the developing versus developed world. More than about 40% of water use in the average home comes from the bathroom, and about 27% of it is used from toilets. Toilet water use can vary significantly. Older toilets can use 3.5 up to 7 gallons of water per flush. We're going down to this holy grail, trying to get to about a gallon per flush in the new toilets. And that is something that, you have this crossover where it doesn't make sense anymore because you have water that is not enough to discharge the waste, so you have to flush twice. What is this toilet with a pedaling thing on it? I was looking up toilets, and this is interesting, right, with regards to future sustainability. Bill and Melinda Gates wants to make number 2 a number 1 problem. So they launched this challenge. It was called Reinvent the Toilet Challenge, and the goal was to solicit creatively designed toilets that could provide sanitary bathroom facilities to the 2.5 billion people across the globe that lack access to sanitary facilities. So they had this contest that required people to design and operate a toilet that needed no electricity, needed no running water, and so they could be used in remote parts of the world. And they wanted the designers to come up with some way to turn waste into something useful, such as energy. And Caltech won first prize, $100,000. This is not what they developed, but it was a solar-powered toilet. It uses human waste to create hydrogen, fuel cells, and electricity. So again, this waste to a solution challenge, quite excellent, without any water, without any electricity. Second place was $60,000, and it went to Loughborough University in the United Kingdom, and then third place went to the University of Toronto in Canada. So the Gates Foundation emphasizes sort of philanthropic value of these. The environmental implications of this are not to be overlooked, right? All of these innovative toilet designs had the ability to improve the quality of life in developing nations, to create more sanitary conditions where there's no plumbing, and then also help recycle human waste into valuable resources that communities all around the world could benefit from, including fertilizer, which could help with crops. That's what the pedal is. You're grinding your own waste and turning it into kind of slurry that's a fertilizer that you then put on your land. So putting all of this together, putting together land use, putting together water in the sewer sense and water in the supply sense, we'll go back to Boston, the pre and post shorelines of Boston. Remember that 75% of Boston is landfill. We're not unique. It's like many coastal cities. The thing with Boston is the landfill overlies a thick sequence of glacial marine clay. So it's laid down in glacial marine parameters. And so this makes Boston one of the worst areas to try to build a city on. You have clay, which you don't want to build on, and then unconsolidated sediment. And historically, we've seen that groundwater and surface water have been coincident. So this is the impetus behind a research program that I've had for 10 years nearly now. I was sitting reading my morning paper back when we read morning papers on paper and drinking coffee, and I saw this in the front page of the real estate section, which was that there's this crisis now related to the sewer and to drinking water, which is that water levels, the groundwater, are declining in Boston. The way that you have historically built buildings in Boston is to put them on these wooden pilings that are gone through the unconsolidated sediment and anchored into the clay. This worked well when groundwater was up pretty coincident with the land surface, because recall that groundwater is anoxic, right? So as long as you have no oxygen conditions, you don't have the oxygenation required to destroy these wood pilings. So now we pave everything. We're pumping all of this water away for the T, for underwater sewer lines, et cetera, and water levels are declining, and that's causing the pilings to rot, be exposed to air, be exposed to microbes. So groundwater is declining, which is imperiling these old, beautiful cities in Boston. Again, as far as the 1880s, the only way to make a building stable here in this weird geology is to put the building on tens of thousands of wooden pilings sunk through the landfill into the clay, which was fine when groundwater was stable. It's never a problem because Boston does not withdraw groundwater. What is the problem? Again, we paved everything, and so we have cracked walls, we have differential settling, we have rotting pilings from mold, oxidation, and bacteria, and our buildings are destabilizing. What is the solution? There's a solution, but there are problems with it. There's two solutions, engineering and nature. One is an engineering nightmare. First, we developed this groundwater recharge system, groundwater redevelopment, essentially. So you have all the storm water from roofs, from everything, and instead of sewering it out into surface water bodies, you cause it to infiltrate into the subsurface, and groundwater levels will rise, making your pilings and your neighbor's pilings safe. The other thing that can happen is where you can't do that, you have to cut the wooden piling way beneath the water table and then replace that section with steel and concrete reinforcements. This is expensive. You can see it costing $250,000 or more depending on where you are. And that's how we make Boston more stable. Side note here, right, because we always in this class talk about the hierarchy of environmental problems. You're bombarded with this is a crisis, this is a crisis, this is a crisis. How big of a crisis did we say water problems are in this region? Should we be petrified and alarmed? No, right? It's not a huge environmental crisis. With these declining groundwater levels, how alarmed should we be about the stability of the buildings? Yeah, right. You could potentially destabilize things to the point where they're not safe. So where do I come in with this? I've talked to you in a qualitative, mostly, way about groundwater, hydrogeology, right? We said that the only way to see groundwater is to drill a well that's really expensive. It can be $6,000 to $10,000 to drill a well, and you have one data point. You get the sediment that you can look at that enables you to see where groundwater, how quickly groundwater is flowing. And it gets you to the level. You can have some groundwater quality points there. But you can't make Swiss cheese out of your study area, so hydrogeology is all math. It's more of an art because you're looking at 3 points or 4 points, and you have to interpolate using calculus, but then also really geologic horse scent to see does this mathematical model make sense. And so when students take these upper level courses, they tend to meet them with much trepidation or, oh wait, this isn't what I thought it was going to be. So in hydrogeology, when I was teaching elsewhere, I identified this network of wells in the Back Bay associated with the campus, and I got permission to use the wells to teach students about the applied aspects of hydrogeology. What is a well? How do you measure the water quality? How do you measure the water level? And how can we answer questions related to this declining water level? A lot of neat student theses and projects have come out of this, looking at tidal influences, looking at recommendations to physical plant for ruptured water mains, et cetera. But it was interesting when I was getting permission to use the wells. I went to physical plant and said, can I please use these wells? They're awesome, they're here, and they're right on campus, and students can do so much with these. And physical plant said, no, because we're afraid the students will come in contact with poisonous water. And I said, no, I can show you the water quality. It's quite good because everything's paid. There's no pollutants here in this area. And they said, no, because we're afraid the students are going to pollute the water. So I go, no, on both ends. But eventually they let me use these wells, and we use them in undergraduate, upper and lower division courses for demonstration purposes and for small amounts of field research. So teaching hydrogeology, geochemistry, that sorts of things, they're typically theoretically taught math that students don't always gravitate to. So now we can go to a situation where students will walk out into the field and be able to do this in an applied sense. What you see here, this is a former student who then became a TA and then went on into consulting. He's looking at these two wells that are right next to each other, and they're drilled to different depths. I don't know how much you remember about discharge versus recharge areas. They're drilled to different depths, and that enables you to see a vertical gradient. So remember, water moves from high hydraulic head to low hydraulic head. And hydraulic head in the field is measured as the level to which water will rise in one of these wells. So if you drop your water level meter down, which Matt is holding there, to the well that's more shallow, and it goes down to 13 feet, beep, have the water level meter go off. And then you drop it down to the well that's drilled to 40 feet, and you drop it down, and the water level is at 16 feet. So the lower you go, the lower the hydraulic head. Which way is the water flowing, up or down, in a vertical sense? The lower you go, the lower the head. Excellent. It's going down. If the opposite happened, where the lower you go in the groundwater, the higher the hydraulic head, right? The higher this combination of pressure and elevation and velocity. So it's higher than the 13 feet, it's beep, 6 feet. Then you know which way is the water flowing. Yeah, up, right? So you have a situation where you can test the recharge versus discharge area of this water system. These wells were put in for construction and for sort of monitoring purposes, but it's kind of neat because we can look at groundwater and what it does in an urban area. Remember we said that groundwater in temperate regions is considered a subdued replica of surface topography, right? So the highs aren't as high, the lows aren't as low, and where you have the point where the land surface crosses over with the groundwater, you have what? What is that? It's a lake, a river, a stream, right? A surface water body. We hydrogeologists love that because it's a free data point. You don't have to drill a well. The land surface is beneath the water level. So we look at this and we look at an urban hydrogeology sense, and it's weird because the groundwater does nothing like what the land surface does. Land surface is pretty flat in Boston because we've carved off the high points. And the groundwater has these weird wavy undulations and then big, huge piles. Why piles? Come on, people, meet me halfway here. Why big piles? Oh, okay, yeah, that could be. Absolutely, that could be. But remember we talked about the ruptured water main? And so water rising up in these weird ways. So it's kind of interesting to try to map groundwater in an urban environment because the paving and the water ruptures from the sewer, et cetera, are making these crazy undulations. So the students are having a great time here trying to figure out what is groundwater doing in this area. It's a really kind of interesting thing to see this. And then also they will look at rudimentary groundwater quality. So remember from our discussion of water that water it has a bipolarity, right? It has a polarity to it, and it has a high dielectric constant. So it picks up the chemical signature of what it's flowing through. And the things that it's flowing through in this region are really strange. This landfill, you have building demolition debris, you have soot, you have ash, really strange stuff. So it's neat to look at the chemistry and to back into what is this water flowing through potentially. And then also you can use the chemistry to see where there are possible sources of contamination. Road salt is a big source of contamination in water in the Boston area. We don't drink this groundwater, so it's not a pressing concern, but it's interesting to make these isohydal maps and to discuss where groundwater is coming from, where it's going to, and how much of a problem it is. So I promised you, and I know you're waiting for me to make good on this promise, to show you a baler. Remember we said that the larger the diameter of the groundwater well, the more expensive it is to drill. And as this course is really a veiled economics course, right, we want to get to the smallest price for our data. So you do really small diameter wells, and that presents a problem when you're trying to figure out how do you get down there and suck the water up. So you can use a pump, a little tube stuck down in a pump, but this is a really cheap way and a quick way to take water samples from these little wells. This is called a baler. this long, thin tube. This is plastic because it's disposable. We'd use it in hazardous waste. It's a long, thin tube, open at both ends, but there's a check valve at the bottom of it, this little steel ball bearing, and it sits at the bottom, and it's essentially a bucket, a long, thin bucket. So you free fall it down into the well, and the force of the water displaces the stainless steel ball bearing, and then the ball bearing settles down when the tube is full, and you pull it up, and in this way you have this column of water, then you displace the ball valve, and you have a groundwater sample. You can bring it to, you can do field kits, or you can bring it to the lab to discuss or to figure out what's in there. So those are the bailers, and you have the string that you pull these up with. So students are able to look at bailers, disposable bailers, anaerobic sampling, sample volumes, hold times, all sorts of things that if you're going into the field, if you're going into geoscience and you're going to be working on a career in industry, you have these situations. Again, with the baler, with the groundwater level, looking at water levels in modeling classes, we take these data and put them into mathematical models. The Fenway, we're a little bit removed from the Fenway, but the Fenway is a really neat point of intersection. Again, surface water bodies are the demarcating line, the edge of one, between where groundwater and the land surface slope off. So you're able to see groundwater. Temperate regions, about 70 to 100% of water in a river at any time is groundwater. So you're looking at groundwater here, and the students are able to see what's going on here. This is a wetland. We've talked a lot about wetlands early in the course. And the really fascinating thing about urban hydrogeology is that wetlands people are habituated to, as you may remember, wetlands being a groundwater discharge area, right? So the water's coming up and out of the surface, from the ground, and making that area wet. Again, that changeover between the land surface and water. Because of this urban environment, because of all the pumping and paving and infiltrating of sewers that we talked about, this is actually, and it's always so exciting when a student figures this out, is actually a recharge area. So there's a lot of clay material at the bottom of this wetland. It's sort of holding water to the surface and is slowly recharging water. And the reason we know that is by putting two wells next to each other. We can install them with our hands in this area because it's just plant material, and figuring out that lower you go, the lower the water table, versus lower you go, higher the water table. It's weird. And we take boots and we go out into the water a little bit, and it's a recharge area. So this ties into everything we talked about today, that water levels in Boston are declining to the point where it confuses we wetland scientists. Why is this like this? So that is why these buildings are settling and groundwater levels are declining on the rate of about 9/100th of a foot per year. Sounds small, but in geologic time, not bad. The students love getting out into the field. People don't even know about these fens, which are walks from their building, looking at the urban environment in a totally different way, thinking about the sewers. Where are the sewers? Where are they going to? Where is our water? And so kind of summarizing the latter half of this is that when you're able to do hydrogeology in a geoscience class, in an applied setting, you're able to interface with people like physical plant, professional geologists, contributing to long-term databases, and really getting sort of hands-on field experience that's invaluable. With regards to the summary of everything we talked about today, it will be very interesting to look at Boston's water challenges of the future. How are we going to fix this sewer problem? The Boston Water and Sewer Commission has a plan to fix it, but it's so big, again, it's going to take about 50 years. And we have this problem with the sewers that is not a problem that you kind of customarily think about when you think about leaking sewers. The sewer water is not leaking into groundwater. Groundwater is leaking up into the sewers. So it'll be interesting to see the challenges that Deer Island will face as it has this overload of water, especially when you combine this with our next topic, which we'll deal with on Monday, starting to look at air pollution and climate change. What's going to happen to our coastal cities as a result of climate change? So water will play an important part, as will the energy and mineral resources that we talked about. So we're a couple minutes early. Sorry I spoke quickly. If anyone wants to stay behind and discuss their quiz with me, please feel free to do so. Have a great weekend. Remember, I don't have office hours today.